The first tutorial I made for Z80 assembly language for the ZX Spectrum was very well received. I was surprised about the amount of interest that there was in it. So I'm going to continue making some more. Let's learn a little bit more about machine code. So in the first one, we covered how to manipulate the color attributes on the screen, how to do simple loops in assembly language, and we took note of how the Spectrum's memory, the 48K model, was arranged. So in this lesson, I want to cover text and simple graphics, how to put that on the screen. So let's start another program in assembly language. I'm using the ZX Spin emulator. We're going to begin it as usual at location 50,000 in the memory, so it's org 50,000 is our first line. Now I'm going to do something a little strange looking. LDA, comma, quote, exclamation mark, quote. Now so far you've only seen me put numbers into registers, never strings. But it turns out that I actually am putting a number into a register, you just don't realize it. If I want to display that exclamation mark, I can type the instruction RST16 and that's my program complete. Now over to basic again on the Spectrum emulator, we're going to type 10 randomize user 50,000 to run the program and run. Oops, it crashed. I forgot to end my program with RET. Of course. RET means return to basic. How could I have forgotten? Okay, let's assemble it again. Run. Now it looks as if nothing has happened, but something has happened. It's just we didn't get to see it because the phrase 0 OK 10 to 1 appeared over the top of what I printed on the screen. So here's what we're going to do. We're going to add line 20 into our basic program and we're going to do pause 0. Now what that means is pause until the user presses a key. Now when I run it, watch what happens. As you can see, I've got an exclamation mark in the bottom left of the screen. And when I press a key, then it returns me to basic. Okay, so it's working. I've got text on the screen. But that's only good for one character. So if I wanted to write the word hello, I could do LDA, comma, quote, H, quote, RST16, LDA, comma, quote, E, quote, RST16, and so on until I complete the word. But that's very laborious. There's another way to do it, and we'll get to that very soon. First of all, let's explain this whole thing about putting apparent strings into registers. Let's change this exclamation mark with the quotes around it to 33. Let's assemble the program again. Here we go. Let's go back to basic and run it. And exactly the same thing happened. So whether I put an exclamation mark in quotes or the number 33, it works. So what's really going on here is the exclamation mark is equivalent to the number 33 according to a standard known as ASCII, ASCII, the American Standard Code for Information Interchange. In this code, the whole alphabet, both upper and lower case, plus all the number digits, plus all the symbols you might ever type, and all the user-defined graphics, they're all included as numbers in the range 32 through to 164. Now, it starts off with 32 is a space, 33 is an exclamation mark, I think 34 is quotation marks, and then on we go through other things. I think capital A is on 65, lowercase a is on 97, I can't remember them all, but you don't need to remember them. To give you a flavor of this, just go back to basic and write a simple program. Now, I'm assuming you know a little bit about basic, so you know what a for next loop is. And you can see what's going to happen on the screen when I do this. we're going to get a row down the left hand side starting at 32, going to 33, 34, 35, and next to it we're going to get the ASCII value, rather the opposite of the ASCII value. The ASCII value is what's on the left. We're going to get what that character actually represents in ASCII on the right hand side. So let's run this and see what happens. And there we go. It shows you every ASCII value and its equivalent. So in the assembler, it's very handy that the assembler doesn't force you to learn all these ASCII values. You can actually put the speech marks in and type the character, and the assembler will translate it into the number for you. So that's good. But it's good to know what's going on in the background. So that's that. Now, I don't like the way it was printing at the bottom left of the screen. I want to print to the top left, and here's how we do that. At the top of our program, underneath org 50,000, what we want to do is load the value 2 into the accumulator, LDA, 2, call 5633. Now, we haven't used call before. We have used JR, which stands for jump relative, and there's also JP. JR and JP, they're pretty much the equivalent of go to in BASIC, whereas call is the equivalent of go sub. There is a difference between JP and JR. It's subtle but important, and we'll cover it later when we're actually using those instructions. Call is like go sub. So in other words, wherever you go to, after it executes the piece of code in that location, it will expect there to be an RET instruction, which is the equivalent of return in BASIC, and it will come back to the place from where it was called. Now, we've already used RET as return to BASIC. It has that secondary function of return from whatever routine that called it. So in other words, if you use call, then the next time RET is invoked, it's going to return that call, and it will only return to BASIC if there isn't a call to return from, if that makes any sense. Okay, so memory address 5633 is very low. It's right down at the bottom of the memory in the ROM. So what's actually going on here? There's a ROM routine in here, and we don't really need to know what it does. All we need to know is that it expects to see the value 2 in the accumulator, and when it sees that value, it makes the next print position the top left corner of the screen, and then it returns you back to the place where you called it from. So if I did LDA, 3, as far as I can recall, that opens up any attached printer peripheral for output. But LDA, 2 is the top section of the screen. So with that in place, let's now compile our program again and run it. And there we go. We get the exclamation mark at the top left of the screen, as expected. Okay. We got one character on the screen, but we want to get several characters on the screen, and here's how we do that. Okay, at the bottom of the program, even beyond the RET statement, I'm going to open up a section of memory called string. That's just a label that I'm putting on it. And I'm going to write def b quote hello close quote. And after that, EOSTR, which is short for end of string. And I'm going to write EQU space $. Right. This is a bit like making a data statement in BASIC. It's outside the normal program instructions, which is why I've put it after the RET. But it's a memory location that I'm simply calling string. I could call it anything, but I'm going to call it string. And I could call EOSTR, I could call that anything. That's really just a little placeholder that allows me to target just after the word hello. In other words, okay, that's not making a lot of sense. It will in a moment. So let's go up, and we're going to take away our LDA33 and our RST16. We'll leave the call statement in because we want the top left of the screen to be the starting point. So what I do is LDDE, comma, string. That will load in the memory location string. And then BC loads end of string minus string. So I'm basically loading the length of the string into BC. And then when I do call 8252, which is another ROM routine I'm calling, it knows what to do and it reads the rest of the string until it reaches the end of the string where it terminates and returns, and it prints it out along on the screen as it goes along. So that, quite simply, is how a string is printed on the screen, and it can be a very long one if you want. So let's run it and find out. And there we go, hello at the top of the screen. Call 8252 basically just expects the registers DE and BC to be loaded in this fashion. DE points at the start of the string, BC is the length of the string, and call 8252 simply knows what to do with it. Now you might be wondering why ASCII codes begin at 32 and not at 0. Codes 0 to 31 are reserved for special functions. For instance, I think code 13 is a carriage return, so that would allow you to take a new line. So let's just test that one out. I'm going to go after hello, I'm going to go comma 13, comma goodbye in quotes. So that should put the word goodbye on a new line. So far so good. There are many other codes that we can use as well. You may remember in BASIC we could do print at, and then we gave it X and Y values so that we could target a specific area of the screen to print on. Well, we can do that very easily as well here, and that is done using code 22. So if I do def b 22, comma 3, comma 11, comma quotation marks hello, what that means is print at row number 3 and column 11 hello. In other words, 3 rows down, 11 spaces across. So it just works that way. 22 will expect to see legitimate values after it. The Y value first, then the X value, and then the message that's due to be printed. Let's compile that and run it. Yep, it works. I should say that I'm in the habit of using the wrong terminology from time to time. I tend to say compile a lot rather than assemble. Compiling a program isn't really the same thing as assembling it, although practically speaking it is. And it's because I have a background in high-level languages. When you compile a high-level language, you're actually translating it from that high-level language into machine code, which the computer can understand. Assembling is different because you are actually writing the program in machine code to begin with, so it doesn't actually have to do any translating. Well, the only translating it's really doing is, labels like string and end of string, they are converted into actual memory register values. But, LDA is an actual value corresponding to a number, an 8-bit number, that the microchip understands as an instruction. And so is call, that's a different number. LDDE is another number. LDBC is another number. RET is another number. They're all just 8-bit numbers. So all the assembler really does is translate those into numbers, and the Z80 processor can understand them. So I hope that makes a kind of sense. There's really no compiling going on. It's all just assembling. And again, I'm calling these instructions, they're really known as opcodes. So LDA is an opcode, and the 2 after it is an operand. That's the correct terminology. And I'll try to stick to the right words, but I'm likely to mess up in that regard. But we'll get to the same result no matter what. Okay. So still on the subject of these special ASCII characters from 0 to 31, we can also use this to change the paper and ink values of the attributes that we're going to display this text as. And we do that using 16 for the ink. So let's say we're going to set the ink to red, which is 2. 17 for the paper. And let's set the paper to yellow, which is 6, I think. Let's see what this looks like. There we go. Pretty simple. And there are obviously other codes that do other things, but these are just the ones that I've investigated for the time being. Right. That is text. Now, what about making a user-defined graphic, a UDG? So what I'm going to do is I'm going to open up another data label here called UDGs. And again, I'm going to use def-b. Can't remember if I explained this or not, but def-b really just means that the information following does not consist of opcodes. It just consists of data. In other words, it's not something that's ever going to be run as a set of instructions in machine code. It keeps it separate. I don't think def-b is even stored in memory. I think it's just an assembler directive. So, you may have fiddled with UDGs in BASIC in the past. If anything, it's simpler to do it even in assembly language. So, let's create a small graphic, 8 by 8, in the shape of a ball or a coin or a counter. And why we're choosing this particular shape will become apparent in a moment or two. So there's a little graphic with the zeros and ones. Zeros are representing the paper, 1 is representing the ink. So let's translate this from the binary digits into actual decimal. Binary is one of those things that you're going to have to learn if you want to get the most out of machine code, I'm discovering. I can still remember how to do it because it was something I was taught way back in school and something I learned even from the books that I was reading about the spectrum back in the 80s. I don't know whether you know how to translate binary. It's something you do need to learn, so I'll cover it very briefly here. But if you're struggling to understand this, I'm sure there are more detailed tutorials. So basically, if I want to count in binary, you've only got 2 digits. So the first binary digit is 0. The next one obviously is 1. But we don't have a 2. So what's the next highest number after that? Well, it has to be 10. Now we don't call this 10, we call it 10 because it's not 10, it's not decimal. So 1 is legitimate, so the next one up has to be 11. Now we can't go to 12 because we don't have a 2, we can't even go to 20. Where can we go? 100. And then we go to 101, 110, 111, 1000. So you see the logic of how this counts up. So these numbers have their decimal equivalent. But if you're faced with a number like 0111110, there's an easy way to translate that into the decimal equivalent. And you do that by laying it out in a table that goes from 128 across to 1, like this, in powers of 2. and we place the binary digits underneath. And all we have to do to get the decimal equivalent of this binary number is to add up all the instances where there is a 1 present. So that's 64 plus 32 plus 16 plus 8 plus 4 plus 2, which is equal to 126. And as you can see, that's the central part of my little graphic, the 4th and 5th lines of the graphic. So there you can see it's def b 0, 24, 60, 126, 126, back to 60, back to 24, and back to 0. And that's how those values were worked out. There's also an easy way to translate any decimal number back to binary if you ever need to do that, which you sometimes do. So let me just take just a random number, let's say 76. What is that in binary? Well, how we work it out is, first of all, we say, can I fit 128 into 76? No, I can't, because 128 is greater than 76. So I start off with a 0 under 128. Can I fit 64 into 76? Yes, I can. So I put a 1 there. And what am I left with when I do that? Take 64 away from 76 and I get 12. Does 32 fit into 12? No, put a 0. Does 16 fit into 12? No again, put a 0. Does 8 fit into 12? Yes, it does. Put a 1. And that leaves me with 4. Does 4 fit into 12? Sorry, does 4 fit into 4? Yes, it does. That leaves me with 0. So the remaining 2 digits must be 0. So 76 in binary is 01001100. That's how it's done. I do recommend, if you're struggling to understand binary, I do recommend you learn how it's done, and it becomes sort of second nature to you. So there's my little UDG, but at the moment it's just sitting there like an arbitrary piece of data. We have to actually put it into the memory where the UDGs are stored within the spectrum, which is right up at the top of the memory in 6.5 something or other. It was covered in the last tutorial. I forget the value. But we're going to do something a little bit, perhaps a little strange here. So let's take a look at this code. LDHL, UDGs. So the address where my UDG information is stored is put into register HL. Now this next line, LD, memory register 23675, HL. 23675 is a system variable that tells the spectrum where the UDGs are positioned in the memory. So when you switch on your spectrum, the address in 23675 and 23676, because it has to take, it's 16 bits to store an address, so it has to take two places, 2 bytes. It's going to be 65,000 and something, right? What these 2 lines of code do is they tell the spectrum that the UDGs are now going to be stored in the memory location indicated by the phrase UDGs. Bear in mind, UDGs is just a memory location that, thanks to the capabilities of the assembler, the user does not have to memorize or know about. I don't need to know exactly where it's stored. I just let the assembler take care of that. Okay? So we're changing the position. This was a little tricky for me to wrap my head around. We're basically telling the spectrum that the UDGs, which are normally at 65,000 and something, will now be at the memory location called UDGs. Okay. And that's basically the work done. Once you run this, the first UDG will be the one stored under 0, 24, 60, 126, 126, 60, and so on. If I wanted to do more than one UDG, I would just continue this list. I would write another def B line and do another graphic. And it would simply fill up the memory allocated to the UDGs. It's not that I have, this is what confused me originally, it's not that I have to load this data into a new place. I have told the spectrum to point at a different place. I've told it to point at this line of my program. So the UDGs are automatically loaded in the same way that if you poke an area of the screen memory, the screen is automatically updated. So it's a really handy feature, this. So all we've got to do to test this is to put a line in that allows me to see that UDG on the screen. Now the UDGs correspond to the ASCII codes 100, I think it's 144 to 164, and there are 21 of them available on the 48K spectrum. So I'm going to do another RST16 command. Let's first load the accumulator with 144, the first UDG, and RST16 will send that to the screen. There we go, perfect. We've got a little ball. Now why did I pick a little ball? So this is all working according to a plan, by the way. I've decided that I want to try and make a computer game version of the board game Connect 4. So this little graphic is going to correspond to the counters of that game. And I also need to draw a grid, which is 7 across by 6 down in the traditional Connect 4 game. Now the handy thing is, I can use the same graphic to do the grid as I'm using it for the counter. All I have to do is invert it, and then it becomes a hole instead of a counter. I just use different paper and ink values. So for instance, the counter, there's red and yellow counters. So all I have to do is ink red, paper white, and I've got a counter. But if I want to do the board itself, all I have to do is ink white and paper blue. And I've got part of the board with an empty space. And as the counter goes into the board, I simply change the ink value to whatever that counter is, whether red or yellow. So one graphic is all I need to make this game work. So my exercise right now is using the skills that you've learned now. Can you write a program that displays the words Connect 4 somewhere along the top of the screen? And in the center of the screen, it draws the board for the game, 7 across and 6 down. And then in the next exercise, the next tutorial, we will put the first counter in, and we will allow the player to move it left and right, and we possibly will get as far as dropping the counter onto the board. Okay folks, thanks for your attention. Hope you're enjoying these tutorials.